Well, broadcast is we're rolling. Looks like all three of us, huh? Not very many people here. What would you like to go through to get ready for this test tomorrow? Do you have any requests or questions?
3.5 and 3.7, I say.
Oh, so part of the. So in other words, you want to go back to some of the lessons. Okay. 3.5. I will go get that. Okay, I'm on the 3.5. What would you like to look at on 3.5?
Could you go through some like the harder question, like the harder one to solve? Yeah.
Okay, well, here I'm looking at. Let's take a look at like 29. So first of all, I got to get in my head what was going on in lesson 3.5. That was, oh yeah, implicit differentiation. So the idea there is if you can't solve an equation just for y, you can go ahead and differentiate anyway. Just got to remember that anything non-x has to be, you have to do the chain rule. So here's one, tangent x plus y equals x. So we take the derivative of the whole thing. The derivative of the tangent of x plus y is the secant squared of x plus y. But then we have that inner function x plus y. Well, we got to take, so the chain rule, what's the derivative of x? 1. What's the derivative of y? dy dx. On the right side, the derivative of x, 1. Okay. So then the whole idea is to try to get dy dx by itself. So the first thing I did is divided both sides by the secant squared x plus y. Welcome, Jen. We're going through a 3.5 question. This happens to be number 29. So I divided both sides by the secant squared. That gives me this. And now all I got to do is get rid of that 1. So I subtract 1 from both sides. And now I've got, basically, this is my derivative. And now, well, you can rewrite it a little bit, because what's 1 over the secant squared of anything? The cosine squared of it. So now we have an even simpler form. And then you're done unless they say find the derivative at this point. And in this case, they told us to do it. You see that up on the top there? They told us to do it at the point 0, 0. So what's the derivative at 0, 0? So you plug in a 0 for x and a 0 for y. The cosine of 0 is 1. The cosine squared is 1. And 1 minus 1, 0. So see if you have any questions on that one. So that's an implicit at a point. So one more time, when you do that, you can just take the derivative as it stands, even with an equal sign in it. When you're dealing with anything non-x, then you have you got to do the chain rule. So up here we had to do the chain rule anyway because we had a quantity in here. So we came down to the secant squared of x plus y. Well, that's the derivative, but you got to take the derivative of the inner x plus y and multiply that derivative of x1, derivative of y, dy dx. After that, the rest was really pretty much just algebra. You have a follow-up question on that one, Richard?
No.
Let's also look at number 33 on 3.5. So 33, we've got this x squared plus 4 quantity times y equals 8. So now we're going to just take the derivative. Oh, yeah, and here's the point. We want to find the derivative at the point, 2, 1. So when we take this derivative, we have to think what? That's a product rule. First times second. So we got to do the product rule. The first times the derivative of the second. The derivative of y is just dy dx plus the second times the derivative of the first. And then on the right side, derivative of 8 is 0. Now we got to do the algebra to get dy dx by itself. So step 1, subtract the 2xy from both sides. Step 2, divide both sides by x squared plus 4. And there it is. There's our general derivative. Negative 2xy over x squared plus 4. I know it looks wrong because you've got y's in there, but that's the way implicit derivatives look. Now, what's this derivative at the point 2, 1? So we plug in a 2 for x and a 1 for y. So that becomes negative 4 on the top, 8 on the bottom. Final answer, negative 1/2. So there's a couple 3-5 questions. Richard, you also, what was it? Did you say 3-7?
Yeah.
3-7, okay. Let's take a look at that. I'm trying to think, what do I need? 3-8 was what? Oh yeah, let's just go to 3. I think I can go directly there. 3-7. Oh yeah, related rates problems. Yep. So you just pick out a sample. Yeah. I don't know. Let's just take a look at number 15. Is it? I don't have it. I can show you the problem. 3-7, number 15. Okay, so there's the problem for 3-7. Here, let me just grab that. Okay. Let me just lock that in place. All edges of a cube are expanding at the rate of 6 centimeters a second. So the edges, we'll call them E for edge, the edge of a cube, is expanding. So that means the rate of change of the edges with respect to time is 6. So dE dt is 6. And you want to know how fast is the volume changing. So that's dV dt. So that's what we're trying to find. And then we'll do the first part when each edge is 2. So we've also been given this E equals 2 here. So I made a little drawing. How do you find? So the big thing here is we got to do volume. How do you find the volume of a cube when its edge is E? Well, it's E times E times E, right? Length times width times height, and they're all E. So there's our equation, volume equals E cubed. So now we do the implicit differentiation, just differentiate, and what are we going to do it with? With respect to time. Almost always, that's the way implicit differentiation problems have to be done. So the derivative of that with respect to time. On the left, dv dt. On the right, 3e squared. And then chain rule, because e is not t, dE dt. Now plug in your given information. We know the edge is 2. So 2 squared is 4. 4 times 3 is 12. The dE dt is 6. And basically, that's how fast the volume is changing at that moment, 72 cubic centimeters per minute. So something just keep in mind strategy-wise. Here's a case where you had to come up with the formula V equals E cubed, but I believe, I'm pretty sure you guys all know length times width times height is volume. And then in this case, length, width, and height are all E. And so part of the challenge is coming up with that equation. The other part is make sure you write down everything that they gave you, which is what I was doing on the top here. And what is it they want you to find? How fast is the volume changing? dV dt. Once you get that down, yep, the problem is pretty straightforward at that point. And you know, some of these get a little bit harder, like for example, number 18 here. Here we have this conical tank, vertex down, obviously. You're gonna have your tank set that way. And then they give you the fact that it's 10 feet across the top. So you can see I tried to draw that out here. 10 across the top. And 12 feet deep, 12 feet coming down. Water is flowing. All right, so now, this is dealing with what? Find the rate of change of the depth of the water. So the whole idea with a tank is it's got how much volume. So we know it's a volume problem. Find the rate of change of the depth of the water. So dH dt. What's the depth, or usually we call that height. So dH dt. When the water is 8 feet deep, you know, the blue is, I'm trying to write, excuse me. The blue circle here is indicating how deep is the water in the tank. And that height is H there. So when H is 8, and they told us that water is flowing into the tank at a rate of 10. So dV dt is 10 cubic feet per minute. So now what relates all of this? The volume. So there's one other thing we got to figure out here, and that is, how do you figure out the, let me think here. Oh yeah, the ratio of the height to the length was a little bit tricky, and I drew that down at the bottom here with this cone. So all the way across was 10 feet. That means the radius is 5. We know the depth is 12. So we've got this 5:12 ratio. So that means, you know, like what? So the question is, what's going on when the water height, let's say, is right there? Okay, well, that radius is going to have the same, I mean, that's 5 to 5/12 of whatever this height is. So this relationship down here, R equals 5/12 the height I needed. I mean, Otherwise, I've got too many variables up here. And notice we didn't really have we don't really have anything given about the radius in the problem. Well, I guess we do. We were told the diameter is 10, so the radius is 5. But the problem is we need this ratio. So anyway, now we take, what's the volume of a cone? It's 1/3 the volume of the same height cylinder. And the cylinder is the area of the base times the height. So this one, I don't know, I'd probably give you the formula for that. So 1/3 times the bottom of the cylinder, pi r squared, or the bottom of the cone, pi r squared, times the height. So there it is. And in place of r, I'm going to plug in this 5/12 h that we figured out down here. Okay, we got to go to the next page here. So to show the detail. So yeah, so here's where I plugged that in. We squared it, and we got 5h squared is 25h squared. 12 squared is 144. So by bringing all of this together, here is, this is the best form of it right here. This is our relationship. Volume equals that. Okay, so now if we take now it's time to implicitly differentiate. So dv dt on the left. On the right, 25 over 432 pi, that's a constant. Pi is a constant, all those numbers are a constant. So we don't really do any derivative there, but we do the power rule on h cubed. 3 comes down, that's where we get the 75. The rest all changes. H goes down in power, down to 2. And then, because h is not small t, I need to do the power rule, dh dt. Okay, now I got to get dh dt by itself. We were given the height, weren't we? Let me go back. Yeah, we were told the height is 8. Okay, so now, right here, I plugged in height of 8. 8 squared is 64. So we get this calculation problem here. We have to take 4,800 pi divided by 432, and we got to divide both sides by that to get dh dt alone. You can see I flipped it over, invert, multiply. And after simplifying, I wound up with 9 over 10 pi. Pi is what, about 3? So it's about 9/30ths. So it's pretty close to 1/3 of a cubic foot per minute. That should be cubic feet. So we were finding, no, that's not volume, that's height. So that's correct. It's feet per minute. Yep. So here's one that's more involved, but not, yeah. So here, I don't know, I think I might have given you the formula just to make sure, because I'm not really testing you on volume formulas of cones. And this one is not as publicly known. So, but then the problem is, you had to do this RH thing. So we didn't have too many variables in there. So that made that one a little bit, you said you wanted a harder one. There's a little bit of a harder one. Excuse me, I'm sorry. I had to go walking the other day when it was 18 degrees, and I think I caught a little thing cold. Okay. So at least there, we've looked at a couple problems from 3.5 and a couple from 3.7. What would you like to do next? Skylar, any questions? Or Jen, did you have any?
No. We've pretty much gone through everything that I could think of. I had issues with.
And by the way, it's too bad that this turned out to be a split up review session regarding, the test. So that's not ideal, but at least it's better than coming in cold tomorrow morning and taking the test, And don't forget, the tutor is offering a session this evening. Hopefully you got that email. I sent a mass email to the whole class.
Question: how long the test will be? Like how many questions?
Well, last time I gave it, I only had 8 questions. So when you look at the review, you're like, holy cow, we could have a test that lasts about a week. But that doesn't really help you though, because you don't know what the question, you know what I mean? So but if you had one of these questions, you can see where that could take up a fair amount of time. Mostly, okay, what did I ask you guys on the quiz? I asked you basically all the different kinds of derivatives. So that's still important. Add to the application questions like this one that we just did. That pretty much is the material for the test. And, we went through all these different kinds of things. Do you guys know, for example, your derivatives of your trig functions? Do you remember how to take the derivative of a logarithm? Do you remember how to do it of a natural log? Those are all. Anyway. So anyway, rough idea. Last time I had 8. Maybe that was a hair short, but somewhere around 10, 8, something like that. So that there's a realistic, it shouldn't be too terrible to complete in 50 minutes. It should work out. At least that's the hope. Well, I think I'm going to just do one more question. I'm not hearing any questions, but on the review, I wanted to go down and do. Yeah, I would like to. This last section, not that this is, it's not like, oh yeah, this is going to be on the test. I don't know that. Honestly, I haven't written my test yet. So but I thought this was an interesting problem. So let's take a look at number 100, tangent lines and normal lines. So you see in number 100, we're given the equation x squared minus y squared equals 20. And you're supposed to find, if you look in the directions there, let me blow this up a little bit more. You're supposed to find the equations for the tangent line and something called the normal line. And the normal line, as it points out in parentheses here, is perpendicular to the tangent line right at the point of tangency. And then when we get all done and we find the equation of the tangent line at the point 64 and the normal line, let's plot them to show really how they look. So, all right. So the first thing we have is this x squared minus y squared equals 20. Let me change to blue here. All right. So we have x squared minus y squared equals 20. And we want to take the derivative with respect to x of that whole thing. All right, so when you take the derivative of x squared, of course, that's 2x. The derivative of minus y squared is minus 2y. But because that's not an x, I also have to do, you got to take the chain rule, the derivative of y with respect to x. And then on the right side, the derivative of a constant is 0. All right, so we want to solve this for dy dx. So negative 2y dy dx equals negative 2x. And then finally, dy dx equals negative 2x over negative 2y, which is simplified what? Right? Because the negative 2's would cancel. Negative 2x divided by negative 2y, the negative 2's cancel. There's your general derivative. Now, what's the derivative at the point, what do they say? 6, 4. Okay, I gotta erase that. Okay, at the point 6, 4. So that's just plug in a 6 for x and 4 for y. You get 6 over 4, which is 3 over 2. So there's your specific derivative, 3/2. All right, so now, when you're doing the tangent line, we just found the slope, right? So we know it's y equals 3/2. The slope of the tangent line is going to be gotten by taking the derivative. Now plug in the 0.64. And plug in a 6 here. 2 cancels into 6 3 times. 3 times 3 is 9. So here is the equation. There's the equation of the tangent line. Okay. Now we got to go on, and we need to do the normal line too. Remember, the normal line is perpendicular to the tangent line. So, normal line. So what do you know about slopes of lines? If the normal line is perpendicular to the tangent line, that means it's what? The negative reciprocal slope. So that one is negative 2/3 x plus b. And now plug in your 0.64 again. 3 cancels into 6 2 times. Negative 2 times 2 is negative 4. And b equals 8. So the normal line is y equals negative 2/3 x plus 8. Okay, so now if we go to Desmos, I just wanted to show you. I've actually got them plotted already. The red, that's the x squared minus y squared equals 20. Okay, and then let's see, where were we here? Trying to find my way back to where we were. Yeah, right there. The tangent line was y equals 3x minus 5, and then our normal line was negative. So if we come back to our graph, there's the 3x minus 5, the tangent line, blue. And it's supposed to be at the 0.64, and you can all see this is the 0.64 right here, right? Yep. So it's on the red curve, and you see how the blue is perfectly tangent to that curve, just touches it at that one point. And then the green, that's the normal, and it's perpendicular right at that point of tangency. So you can see that checks out real nicely. So I just wanted to show you that one. I don't know, I don't know if you've ever heard that, but normal line, and if let me just go back to that problem on the. So if I was to give you one like this, I'm not saying I will. I'm just saying if I was, I like the fact that they told you what a normal line is. So you didn't have to know that. They told you. And okay. So So what I was hearing from you is you really don't have any other specific questions. Is that correct? I just want to double check. Did anybody have anything else you'd like to bring up? I hope, by the way, I hope all of you, I hope the three of you, or now it's, yeah, the three of you had a good break. And I look forward, we'll see you tomorrow. I'll have a test for you. It's not like it's not going to have real many questions on it, but hopefully we can get this derivative review chapter completed successfully. Well, thank you, and I'll see you tomorrow.